next week's sprint. So make sure that all the tasks that need to be up in the backlog, prioritized as needed, are in there and have definitions of time ready to go. It feels like the tech art is starting to lag behind the engineering. So also be prioritizing the rate at which I look for a full-time tech artist too.
Okay, class. Our break time is now over. So now let's go back here.
Yes.
Now this time what I did was I erased everything.
Now
I'm not
setting up a playable graph to integrate the blending of expression animations with the timeline animations. I got that working pretty well, but hit a bit of a snag in the afternoon when I went to actually write the custom blending function. At some point along the line here, Unity has deprecated the ability to get curves from an animation at runtime. You just don't allow you to do it anymore. It all happens in the C++ side of the engine, and the C# function is still there, but it only works on legacy animations. It doesn't work on new stuff. There's a utility to get those curves, but it is editor only, so you can't use it at runtime. So I'm unable to write custom point function at this point, which means that translation and rotation animations are blending great, but sprite swapping is not blending properly because they're getting strings. So a couple of potential solutions here. Separating them out into individual animations so I can serialize which curves are in which animation in the editor, and then I have to look at the curves at the time. Or having sprite swapping working on a completely separate system outside of the animation system. I'm not fully haven't fully understood the ramifications of those two possibilities, so that's what I'm looking at this morning, is trying to figure out what going forward is. I also Brian, I don't know the next time Brenda is available, but if we could check in with her early next week about like her exploration of plane shapes versus sprite swapping, because plane shapes will work with this system out of the box without me doing anything stuff. So if that's the direction we're gonna go, we probably shouldn't spend a ton of time making some sprites.
Okay, yeah, I'll put something on the calendar for Monday. I guess part of the reason why I wanted to put a good amount of time into sprint prep today and over the weekend is just so that things move really swimmingly on Monday, so that we have time to do a certain thing, because Mondays and Tuesdays are the days that we can definitely have Brenda's time. But yeah, agreed, I'll put something on the calendar right now. Okay. But yeah, thanks for that. Actually, I won't spend any time on the sprints. Real quick question on this. How does sorry, forget if it's a pose or an expression, but if we're saying that the output is going to not be a sprite, but actually a manipulation to a skinned mesh render with blunt shapes, what would be different?
So that what's happening right now is that we have in my example, we have two animations, and they both have transform data and sprite swap data. So if I saturate the weights so that we're either fully on one expression or fully on the other, it works fine. But during that transition period where we're like 50% in one and 50% in the other, the transform data interpolates smoothly between the two animations, but the sprites do not.
Just a hard switch.
Well, it's not even a hard switch, unfortunately, because it's interpolating that float, which is then being converted into an hence, which is then being used to look up the sprite, and there's no sprite associated with that jump data, so the sprite just disappears. So there's avenues to fix this and make it work, but they're all relatively complicated.
Okay. Yeah. And then by using blunt shapes, you can really just interpolate.
Yeah. Blunt shapes would be a lot simpler because they are both small.
Yeah. Okay. Cool. I'll put something on the calendar then. Okay. Okay. that's all I have. On those updates in the channel. I guess if there's anything else that's kind of blocking me, Chris, I think I'll be in the office in the next hour, and we'll probably be able to help with engineering support if you need it.
Yeah, I'm going to wrap my head around this a little bit more this morning and this afternoon.
Sweet. And then tell us where you're going to come by the office today or no?
Yeah, I'll be in later. I'm just wrapping up some work here.
Cool. My sister's working from the space too today.
Okay, cool.
Alright, that's all I have.
Cool. I'll see you later.
Okay, see you guys.
The slippers.
I had to test
This
something.
guy is equal to 2x. We know that. That's the power rule. The power rule of derivatives. So the derivative of x squared is 2x. But here we don't have x squared. We have sine of x squared. So in this case, to apply the chain rule, what do you think we need to put here? So this is now equal to d of
What was he? Did you not see him?
sine of x squared, sine of x, and then this whole thing squared. And then we have now, and then we push the dx aside. Let's apply the chain rule. What do you think we need to put here and there? Over here and there, what do you think we should put? Can you tell me?
He's explaining.
What do you think we should put here and there? This is going to be d of what?
X squared
And
also?
you have x squared? No. You're not going to put x squared. If you put x squared, it doesn't work. It does not work. So if you put x squared in there, then we get this. If you put x squared in there, then what we get is this: d of sine of x squared, sine of x squared, and then we try to take the derivative of this guy right here over what d of x squared like this. Then what is that? Do you know this? Do you know this guy? I mean, look at these formulas here. Does it look like this, or does it look like this? What we have right here is, you mean this guy right here? This guy, does it look like this, or does it look like this? We need to have an exact match. If you don't have an exact match, then we can't get it. So what is that? This guy right here, does it look like this, or does it look like this? Or it doesn't look like either one? What does it look like? Doesn't look like either one. The question is, what is it that we have to put in here? In this, let me put this in orange. What is it that we need to put here in order to have any kind of match? What do you think? This is what you need to know. Nobody will tell you what you need to put here. So, what is it? What goes inside that orange box? Note that this is sine of x squared. This is something squared. So we are trying to take the derivative of something squared. So we are actually trying to take the derivative of this guy. But we don't have an exact match here. So what is it that we need to put into this yellow box? Can you tell me? What do we need to put in that yellow box?
X
Can you
squared.
tell me?
X squared.
Look at this formula right here. Look at this formula. You have to look at this formula right here. Look at this formula right here. Yeah, look, we are trying to apply this formula.
What?
Well, we don't have a match here. This is sine of x squared. We have x here. It doesn't match. So we have sine of x squared. And now what do we need to have here in the orange box so that we can have a match here?
X.
Note that this x right here, this x can be anything. This x right here, this can be anything. So what do you think this x should be in our case? What do you think? This must be what?
Sine of x?
Sine x, you're right. Must be sine x. This one, orange. This orange is too. How about if I just put this in red? And then this one, we need to put sine of x also. Now, if you put that sine x in there, then do we now have a match? Yes, we do. Now we have a match. What formula are we trying to match here? We are trying to use this formula here. We are now trying to apply this formula. Except instead of x, we now have what? Instead of x, what do we have? We now have sine x.
His stick is in there.
If you replace the x and x by sine x, a triple match. All these x's are now all sine x, and now we have something to write. This is now going to be what? 2 times sine x. So therefore, this is going to be what? This is going to be 2 times sine x. 2 times sine x. Oops, in black. And then times, what is d sine x over dx? That is just a regular derivative of sine x, and that's just cosine x. And so that will be what? Cosine 2x, if you like. Sine 2x, writing sine 2x is not required. If you write sine 2x, that's good. You will get full credit. If you just write 2 sine and cosine x, you will also get full credit as well. So I'm not going to expect you to do the last step, but obviously the last step is more concise, so that's better. But not required. Any questions here? Do you get this? And this method, this last method which I've done right here, this is actually what we need in the next section. Again, this last method I've done right here, I'm preparing you to get to the next section, because this is exactly what we'll do in the next section. This process is called implicit differentiation. It is a variation of chain rule. So now I have presented this solution in about 3 different ways. What I want you to do is I want you to learn all 3 different ways. All 3 ways? Yes. Okay, now let's look at number 4, example 3. So what I'm going to do is this. Now I'm going to reinforce this. Let's now look at example 3. Example 3 is this. I'm going to now, not in prime notation, I'm going to do this example 3 in 2 notations. One is in that Leibniz notation, okay? And then the second method will be the last method, which is using that implicit differentiation notation, okay? Okay, so now I'll just show you. Now you don't have to know what these names are, okay? These methods don't have official names, but that's what it is, okay? So now this one here, this one, what is this? Y is equal to what? Y is equal to, in this case, x squared minus 1 to the 5th power. Okay, so that's what y is. Or you know what? Let me write y plus f of x first. Maybe that will make it clear. So this is equal to now, y is equal to f of x. And that is the f of x, and that is equal to this, x squared minus 1 raised to the 5th power. So we have this. So the x squared, and then to the 5th power. Now this is equal to, we can call this guy w to the 5th power. If you call this guy w to the 5th power, then what is w? The w is equal to now what? Is x squared minus 1. Can you write it that way? Yes, we can. So now then, what is now then f prime of x? F prime of x, since f of x is y, we can just call this guy y. This guy is actually dy over dx. And write it this way, since we wrote y plus f of x. So f prime of x is basically dy over dx. But now, what is dy dx? Now, if you look at this guy here, y, however, is written in terms of w. So it looks like we can now rewrite this, apply chain rule. Apply chain rule, so we have what? Dy over, not dx, we push the dx aside. Now, what do we want underneath the dy? Can you tell me? What do we want under the dy? Note that y is equal to w to the 5th power. So what do you think we want to write here? We want dy over what? We want to take the derivative of y with respect to what variable? Can you tell me? Anybody? What do we have to put in here? Box right here, what do you need to put in? Apply chain rule. Note that y is equal to w to the fifth power. So we want to take the derivative of w to the fifth power with respect to what?
X squared minus 1.
What?
X squared minus
What is it?
1.
What is it again?
Is it X squared minus 1?
You want to do it this way. This is actually the next way I wanted to do, but you can do that. You actually want to do this. You want to actually put this guy in here. Yes, you can if you do that. So you put this. Okay, so let me just put that there. You know why? That's a good thing. But that's actually the second way which I wanted to do. This is the method by implicit differentiation, but they're very similar. This is all a variation of chain rule. The only difference is how we write it. So now in this case, what we have is we have dy. We have dy. Now in this case, what I'm going to do is I'm going to write it this way. That is dy is correct, but let me hold that off, okay? For now, and so now in this case, well, what is x squared minus 1? X squared minus 1 is actually w. So in our notation, we just want to put t to dw, which is the same thing as d of x squared minus 1. But in this case, we actually, you introduce the letter w, so we can write it like this. Now y is equal to w to the fifth power. What is dy dw? Now we have y equals w to the fifth power. We want to take the derivative of this w to the fifth power with respect to w. So that will now be 5 times w to the fourth power. And then times, what is dw dx? Well, w is equal to x squared minus 1. dw dx is simply 2x. So almost done. So now what is this equal to? This is now equal to 10 times x times w to the fourth power. It must be, the final answer must be written in the original variable, not in the variable we introduced. This could be called w, or it could be called t, or it could be called z, or it could be called any other letter. So now what is w? W is x squared minus 1, and so the final answer is this right here. So this guy right here, the final answer is this right here. So let me just put a bar here. Now this time what I'll do is I'm going to now slightly, apply different notation. The f prime of x, let's look at this. What is f prime of x? F prime of x is equal to this. Is equal to d of, how about this? You know what? Let me save a step. This is equal to d of x squared minus 1, x squared minus 1 to the fifth power. And then this, take the derivative of this guy with respect to x. So we actually get this, dx. And so then we apply the chain rule. We have included this guy and this guy. Again, that's the chain rule. So the original problem is d of x squared minus 1 to the fifth power over dx. So here I could have written y, but just to make it clear, I wrote this. So if you write that down, then what do we get? What is this guy right here? What is this first term right here? What is this guy? Oh, that is like taking the derivative of x to the fifth power. So do you see that the derivative of d of x to the fifth power, that is the derivative of x to the fifth power with respect to x. What is that equal to? What is d of x to the fifth power with respect to x? Oh, this is equal to 5x to the fourth power. So in order to apply that rule, what did I do? We create this guy, d of x squared minus 1. That's what we create. So when you create that, this guy right here, and this guy right here, are we now ready to apply this rule right here? The power rule? Yes, we are, because we now have a match here. So this is now going to be what? This is now going to be, this is now going to be 5 times x to the fourth power. But it's not x, it's actually this, x squared minus 1 to the fourth power. And then now times the derivative of x squared minus 1 with respect to x, so that guy is 2x. And so you simplify this, you get exactly the same guy. 10x times x squared minus 1 to the fourth power. All right?
Mr. Lee,
yeah, any questions here?
do we have to write the DW, like dimensional analysis thing, when we do it on the test or quiz? Or can we leave that out?
You have to show me the middle work somehow. You have to either show me the work in composition form, or this form, or the Leibniz notation form, or in this implicit differentiation form. This is the implicit differentiation form. This is the Leibniz notation form. And if you want to use that form, like f of g of x, and then times g of x, that's a prime notation form. So you have to show me at least in one form. You want to show me this form, or you want to show me this form, or you want to show me that form. You have to show me at least one form, so that every step is immediately clear. Now remember, the rule is this: every step must be immediately clear. It's not the same as saying it must be correct. Everybody gets it correct. Yeah, not everybody, but most of you get it correct. But many of you don't show me work. So you have to show me some work. So now, of course, if you do this directly, we can actually do this without showing any work, and that is, and then what is this? Y is equal to, what is this? This is y is equal to, this is x squared minus 1 to the 5th power, so this is something to the 5th power. So that is equal to 5 times what? 5 times x squared, and then to the 4th power. So that's going to be x squared minus 1. So if we treat this x squared minus 1 like a letter, like x, then the derivative will be 5x to the 4th power. And then now times that which we treat like a single letter, you now have to take the derivative of that, which is 2x. So you want to do one step like what I'm doing right here. It is one step. But you know what, on the test, just show me some work. Yeah, I don't think I can let you just skip all the work, okay? So that's, yeah, you can't do that here. Now, you know what, example 4? Example 4, yeah, this one, there's so many steps involved here, so we can actually do this in one step. Now, in order for you to do one step here, let's do some groundwork. Let's say we have a function g here, and this is g prime. So how about this? How about let me, sorry. This is undo. So undo here. How about if you have a function? How about if I create a function here, and the chart is going to be this. We have, let's say, g here, and let's say this is g prime, the derivative, okay? So now, if g of x is equal to square root of x, what is the derivative? It's 1 over 2 square root of x. 1 over 2 square root of x. And then now, let's see, what other functions do we see here on this example 4? We see cosine. Now, what is the derivative of cosine x? The derivative of cosine x is equal to minus sine x. So we need that. We need minus sine x. And then what other function do we have here? Oh yeah, we have x squared plus 1. What is the derivative of x squared plus 1? X squared plus 1? Well, that will be, what, 2x. Okay, so now we are ready to go. These are functions involved here. So what is this here? Now, what is f prime? So from here, now let me do this in one step now. This is f prime. F prime of x, again, class, I'm going to do this in one step. Watch out. Okay, watch what I'm doing here, f prime. So if you look at this here, f of x equals something, note that this is f of x is equal to square root of w. Square root of something. That means you have to apply this function. So the derivative of that is that. So we get 1 over 2 times the square root of x. But in this case, it's not x. It's actually cosine. It's actually cosine of. So now, you know what? That let me color code this. How about this? This is actually cosine. So now, let me write cosine. Because it's not x, it's really cosine of this. So now let me write this in, let's say, in red. So we have cosine of what? Cosine of square root of x squared plus 1. Yeah, so it's really messy here. Now, times, we now have to multiply by the derivative of what's in red. Cosine of square root of x squared plus 1. But this is cosine of something. What is the derivative of cosine? It's minus sine. And so now what we have is, we now have minus times, we now have times minus sine of something. So now let me write minus sine of something. Minus sine of what? Is it minus sine of x? No, it's not sine of x. It's actually, now let me color code this again. So this is now going to be square root of, square root of, some minus sine of, cosine square root of x squared plus 1. So we treated the square root of x squared plus 1 like a single letter. Okay, so now what? Times. Now we have to take that expression, which is a single letter, which is square root of x squared plus 1. We have to take the derivative of that. Now, what is the derivative of square root of something? That's this again. So that will now be, let me color code this in red again. This is now going to be 1 over, you know what? Let me erase this part. So this is now going to be a times. This is now going to be times, what times? The derivative of square root, which is going to be 1 over square root of 1 over square root of 1 over 2 times square root of that, which we treat like a single letter, but it's not x, it's really x squared plus 1. So now let me write this in x in red notation. Red color font and times this plus this. And then times this, and now times what? Now times the derivative of x squared plus 1, which is now equal to 2x. So this is now the final answer right here. Now you may say that this is too messy, right? Okay, now how about this? I'm going to do this example one more time this time, and I'm going to slow down one step. So what I'll do is I'm going to now what? I'm going to clear this. I'm going to say clear this. So what I'll do is now this. How about number 4? So I'm going to call this guy y. So what we will have is we will have dy over dx. No, right. Now one. Let me slow down here. I'm going to slow down one step here. This is what I'm going to write. Y is equal to, and then this will be f of x. And then we can write this f of x. Y is the f of x. What is f of x? F of x is this whole thing. So this is equal to now square root of something. So I'm going to write this as square root of what? I'm going to write this square root of w. Okay. Now what is w? Can you tell me? What is w? So I'm going to write y is equal to the square root of w. What is square root of w? What is w? Now, can you tell me what w is here? What is w?
Cos square root of x squared plus 1.
Right. Now I'm going to write as cosine, and now I'm going to I'll call this guy cosine v. Now you tell me what is v? What is v?
Square root of x squared plus 1.
Right, now you call the square of t. Now what is t?
T is x squared plus 1.
That's right. In this case, we have a what? We have a composition of 4 functions. It's a 4 chain this time. So now it's going to be like this. So now what we have is, well, I'm going to write dy over dx is equal to dy, and we have d over dw, and we have dy, dv, and then we have dt. The dt, dy, dw, dy, was dw, dv, dv, dt, and dv, dx. So we have really dx. We have dy, dw, but not dw, dv. That's what I forgot. I forgot the dv. dv, dw, and then dv, dw, dv. Oh no, wait a minute. dy, dw. dy, dw, dv, and then dt. There we go. Then dt and the dx. So now what I'm going to do is now this. Now we have dx, and then I need to put dw here, and then I need to put dv here, and then dt here, and then dx here. And now what I'm going to do is I'm going to now put this here. I'm going to put this right here, and now put a fraction bar here, fraction bar here, fraction by here, a fraction by here, a fraction by here. Then I'm now going to put this guy right here. What is it? So we have a 4 chain. Times, 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 times. Now what is dv dt? dv, what is dv dw? See, no, dy dw. That's a y there, not a v. dy. Yeah, this is a y. That's a y. dy y is equal to square root of w. So what is that? That will be 1 over what? 1 over 2, and then square root of w. Now what is dw dv? W is equal to cosine v. So what is dv dw? That will be minus sine v. Then now what is dv dw? dv dt, dv is equal to square root of t. So what is now dv dt? That will be 1 over 2 square root of t. Then now times what is dt dx? So t is equal to x squared plus 1. Well, that will be 2x. Almost done. Except these variables, intermittent variables here, these middle variables, w and v and t are not allowed on the final answer. So therefore, this one will just replace. This is equal to now 1 over 2, and then square root of, what is w? W is this whole thing right here. This is cosine of square root of x squared plus 1. So that's the whole thing. That's the entire w in x. Then now times, I'm not going to simplify this here, minus sine of v. So what is v? V is equal to square root of t, but t is equal to square root of x squared. So v is equal to, what is v? V is equal to square root of x squared plus 1. Get that. And then you know what? Let's just, reduce the 2 and the 2. If we just reduce the 2 and the 2, we get this, 1 over, what is square root of 2? Square root of t, this is x squared plus 1. Oh, and then we can write times 2x. You know what? Just keep the 2x there. I think if I don't put the 2x, it might be a bit confusing. And then after that, we can reduce the 2 and this 2 right here. And then if you reduce the 2, then you can write the answer. The minus can come to the front. So there we go. There's the final answer right here. So I think this notation is probably the best. Okay? So now let's look at example 5. Example 5, find a tangent line to the curve y equals x times x squared minus 3x, and the plus 1 plus 5. So at x equals 1. Okay, so let me do this here. Now, if you look at this function here, y equals x times this is actually a product. What is the leading rule we have to apply here? What is the leading rule? The first rule we have to apply is what? Is it the power rule? Or the chain rule? What rule? What is the rule we have to apply here? So I'm going to do this in a few steps, okay? So we have this big item here. Okay, so what we have is, okay, so this is now going to be this right here. So from here, everybody watching? So now we want to find dy over dx. You have to take the derivative of that y with respect to x. Now, if you look at this expression y here, it's actually a product. So the leading rule will be the product rule. So we apply the product rule. So product rule, I'm not going to apply it directly. I'm going to now write the product rule form. We type f prime, and then we now have to take the derivative of this. And the second expression we just copy. X to the 4th power minus 3x, and then plus 1 to the plus 1 to the 5th power. This guy, we just have to what? Keep it there. So f prime g, and then plus f e prime. So we now have to take the derivative of this guy, but I'm now going to just copy that down. X to the 4th power minus 3x, and then what? Plus 1 to the 5th power. And we now have to take the derivative of this one, but I'm going to write it out first. This is 5th power here, and we now have to take the derivative of this whole thing, and then I'm going to mark it derivative right here. So this is what we have to do. So this is a derivative. Derivative here, let me just put in the triangle there, just to make sure. We have to now take the derivative here. Okay, so now let's apply this here. What is this? We take the derivative of what? X is 1. What is the derivative of x? That's 1. So that is going to be 1, and then times what? Times x to the 4th power minus 3x, and then what? Plus 5. Plus what? Plus 1. Oh, did I forget a 1 there? I guess I did. I did forget one there. It kind of like this, and then to the 5th power, and then plus, it's going to be x times, it's going to be x times, or that, now we have to take a derivative of that. That will be 5 times x squared, x to the 4th power, minus 3x, and then plus 1, and then to the 4th power, and then the derivative of that, which is going to be now 4x cubed minus 3. So now let me fill in the stuff here. What I need to do is I need to put the 5th power here. There must be a 1 there, 1. And then this x, and then times the derivative of that one, there's only 4th power here. And then this one is a 4th power also here as well. Then now what? And then now the derivative of that, which is 4x cubed minus 3. So this is now the final. So this is the derivative. Any part is not clear, then you have to work on each part separately, and then you can put it back in. So let me put the green box here. This part right here, this part right here, this part right here is actually the same as this part right here. This is probably the most complicated part. So this is like x of 5th power. What is the derivative of x of 5th power? That's 5x of 4th power. That's 5x of 4, but it's not really x. It's x of 4 minus 3x plus 1. Now we take the derivative of that 4x cubed of 4x of 4th power minus 3x plus 1, and that will be 4x cubed minus 3. Now it's done. And now what we have to do is now we have to evaluate that 1. So what is now dy? Now what is now dy over dx? Then evaluate 1. We write it this way. We draw a vertical line here, and then write x equals 1. So this is like f prime at 1, if you like. So if you call this guy f, then this is now called f prime at 1. Or sometimes we write it like this. Okay, plug in 1 here, what do we get? Plug in 1 minus, oh, I forgot to put a 4th power there. What is it? 4th power? Where is it? We have to put the 4th power. Okay, now plug in 1, what do you get? Plug in 1 there, 1 minus 3 plus 1 is what? Is minus 1 to the 5th power. Actually comes out to be minus 1. So that whole thing becomes minus 1. It's actually minus 1 to the 5th power, which is minus 1. And the plus, what is x? X is 1. So that x we don't need to do. But anyway, just put it. Now 5, we have this. And now what is that? That is going to be x to the 4 minus 3. That will be minus 1. But then minus 1 to what power? 4th power. So that comes out 1. And then times, plug in 1 there, or that comes out 1 again. Oh, there's so many 1s. If you do that, what is that? That will be minus 1, and then what? This is 1, 1, 1. This is what? This is actually 5. So this plus 5. So this comes out to be 4. So what we have is the slope is 4, and what's the point? Well, the point, we didn't find the point. If you plug in 1 in there, then what's the y value? If you plug in 1, then we get we get minus 1. When x equals 1, the point is minus 1. The point is 1 comma minus 1. And so what is that? What is it now? This is now equal to y. Y is equal to what? Y minus y plus 1 is equal to, the slope is 4, and then times x minus 1.
That is cold.
So the answer is this guy right here. Yeah, you can simplify that. If you simplify that, what do you get? If you give me the answer in slope point form, like this, I will accept that, okay? Again, slope point form on the test will be acceptable. So if you give me the answer in this form, that is considered reasonably simplified, so I will accept that. Otherwise, if you can simplify, this is x equal y equal 4x, and what? Minus 4, and the minus 5. Of course, you can always check this, or what? You can always check this on your graphing calculator. That's one way to check. Okay? So now, that is the end of section 2.4. Now we have a little bit of time. I would like to start section 1 problem on section 2.5. This 2.5 is just an extension of what...
Professor, but are you sure that it leads to -1 plus 5? Because
well, I think that's -1 plus 5. What's the problem here? It's not negative 1 plus 5. Did I make a mistake?
Because if you multiply with negative 1 and 5, you get a negative 5.
So negative 1 plus 5. Negative 1 plus 5. This whole thing is 5. This whole thing is, this is now plus. Why is it plus? Because this guy's a plus. Why is that one plus?
I think he may be looking at the negative 1 to the 4th power, which would just be positive 1.
Oh, that's to the 4th power. You can see it.
I can't. Yeah, I can't see this. I can't see the
Because
screen.
this is x to the 5th power. If you take the derivative of x to the 5th power, it's 5x to the 4th. So 5x to the 4th. So this is 5x to the 4th power. There you have 4th power. When you plug in x plus 1, you actually get negative 1 to the 4th power. Yeah, that's right. So maybe that 4th power was not there. So how about if I this? Let me erase this the horizontal line.
Professor, can you scroll up a little?
What?
Can you scroll up a little? We can't see the bottom.
Bottom?
Yeah.
Oh, you know what? I don't know. I don't think I can pull this up.
Okay.
Can I see the bottom here?
No.
Oh no. Well, I cannot change notes here.
That helped. That helped a little. Yeah, there you go. Okay.
You cannot see negative 1 plus 5 equals 4. You don't see that?
Now we can.
How you can? Okay, all right. Then that's it. So that's all you see. That is the bottom line. So anyway, you know what? There are a lot of calculus involved here, so it's a bit complicated. But you have to keep track of all this, okay? So how many steps you write, depends on how much you can handle, okay? Now what I like to do is we have a few minutes here left, and so I like to what is it? Did I save this page? Okay, let me just save this page and clear this. And now what I would like to do is I would like to just do one problem here on the next section. Because, wait, do I have only 2 minutes left? Should I even bother to do one problem on the next section? Or should I stop here? You know what, let me just open up. Section 2.5, this is how it looks like. Wait, what section is this? What did I open? Section, what I meant by this is 2.6. Yeah, we did 2.5 already. Now it's 2.6. Now 2.6, now we get into this. Now, section 2.6 is now implicit differentiation. And if you look at these implicit differentiations here, now what do you see? What is the difference between all the previous sections and this section right here? We now get into these guys here. We now get into this, annotate, and then this is what we see. We get into this. You have x squared y, and then we now have to take the derivative of that x squared y with respect to x. Then we have x squared y, we have to take the derivative of that guy with respect to y. And then we have x squared y, we have to now take the derivative of that guy with respect to t. Okay, so we get into these guys. Okay? Why do we want to do these calculations here? Because example 5, there is a circle. If you have a circle, let me just draw a diagram here. A circle, it kind of looks like this. And the circle equation is this x squared plus y squared plus 25. The question is, how do we now take the derivative of how do you take the derivative of a circle? So let's say we want to find this guy. Let's say this guy, what is the point? Or let's say we have another point. How about if you want to find this guy right here? In this case, it's actually over. You know what? Where's the point 3 come up for? Let me see. This one here. Let me just introduce the question. We don't have time to do any problems here, okay? But we have this. Now, where's the point 3 comma 4? Oh, this is a circle radius 5. So what we have is we have a circle radius 5 here. And now where's the point 3 comma 4 is somewhere here. 3 comma negative 4 is somewhere here. 3 comma 4, yeah, somewhere here. How does the line look like? The tangent line is going to look like this. It's going to look something like this. But the question, how do you find this line? How do you find this? The question is, how do we find this line equation here? Now the only problem is, can you write the circle equation as y is equal to something? Can you write it this way? The equation given is what? The equation given is, well, x squared plus y squared equals 1. X squared plus y equals 25. So can you write it this way? All the other methods we have studied so far, up to section 2.5, we must have the function written in this form right here, y equals something. But in this case, can you write it that way? Can you do that? That's the question. And so that's why we have this equation. We have this implicit differentiation. This is equation on an this we have to now find the tangent on an equation which is not a function. So if you look at this graph, if you look at the circle here, this is not a function. It is a relation. So this circle is a relation. So let me see. This circle is a relation, not a function. Not a function. So that's where the problem comes in. Okay, the time's up here. Let me stop here. Again, the quiz is available right now. So all of you must take the quiz. Everyone must take the quiz. Take me the quiz number 4. Is it quiz? Yeah, quiz 4 today. And then I want you to start before 9 p.m. You can or you can start before 9 p.m. We can start now. Okay, you may start. Okay, immediately after this class. Immediately, this class is over. This class is over. Okay, all right. All right. Well, the class is now over, so you can start right now, right? You know what? Can you start the quiz right now? Yeah, I think so. I think I made the starting time. I made the quiz available at 10:45, so you can start immediately. Okay. So again, this quiz is a little bit longer, and make sure that you think a little bit before you just scribble in the answer. Okay. So you have to think first. Otherwise, you might mess up the entire problem. But you know what? It's not that long. It is a bit complicated though. Every one of these 3 problems is a little bit longer. Okay. Okay. So all of you have a good day and a happy quiz and a good weekend.